Hello, my name is Greg Belgrad, and this video is the wrapper for test 2. And the whole point of wrapper videos is to go over, for us students to go over questions that might have given other students a little trouble on the exam itself. And we're supposed to go over the questions step by step and help try to solve these problems and help kids learn from their mistakes and show what mistakes might have been made. So I'm going to go through this problem step by step, and the problem specifically is number 2 on the exam, and I'm going to go through it and help try to answer some questions many other students might have. So the problem statement begins like this. A long thin metal wire with radius r and length L is surrounded by a concentric long narrow metal tube of radius r. Insulating spokes not shown in the diagram hold the wire in the center of the tube and prevent electrical contact between the wire and the tube. A power supply is connected to the device as shown. A power supply maintains a charge of plus Q on the inner wire and minus Q on the outer tube. Like a spherical metal shell, the field produced by the cylindrical metal tube is zero at every point inside the tube. Determine the potential difference between the inner wire and the outer tube, V2 minus V wire. So here's a diagram as shown. You have the actual tube itself, and you have the little metal rod in it, and the electric field inside the metal rod's obviously zero. So you have the length of the tube, you have the charge difference, you have the radii, and you have the power supply. So we want to start with this term. So you have to start out with the potential difference integral for this case, because it differs from little r to big R. So it's minus the integral of the electric field multiplied by the differential length. So you start out, you integrate from minus integral from, you're integrating from little r to big R, so you're integrating from the little radius to the big radius. So you want all this space inside the tube minus the actual volume of the wire itself, because it doesn't matter. So you have to start out with this term 1 over 4 pi E naught, which is the constant for most electrical field formulas, and you have to put a 1 over L here, because as the length increases, the potential difference decreases. So you have to have that L right there, and then you have to have the charge, which is 2Q. These are two charges, and you have to do 1 over R dr, and I'll explain why that comes into play later. So since you're integrating in terms of R, anything that does not have an R term, you can move out of the equation. And in this case, the 2 and the 4 cancel out, so you're just left with minus Q over 2 pi E naught L. And you're still integrating from little r to big R, and that's 1 over R dr. So then when you do the integral of 1 over R is ln of R. So you still have the same term you had in the beginning, but now you have ln of R, or big R over little r. And you can get rid of that negative sign by switching little r and big R in the ln term, which is just, which is a definition in math, but I don't have that in front of me. But if you switch it, it's just a logarithmic rule. And as expected, this is smaller than that, so you'll get a negative term here, so the potential difference is going to be negative. So that is how you solve the integral. And it is a little complicated, I must admit. It gave me a little bit of trouble on the test, but it's just a matter of following the formulas and plugging it in as such. So there's how you actually do this problem. I hope this helped. Certainly helped me when I did it, and I want to wish you all luck on the next test. So study hard, guys.